Hi, welcome to our talk. My name is Marty, and this is Yash. And today we're going to talk about what it was like to scale Pinterest from 0 page views per month to billions of page views per month in just about a year. And in particular, we like this talk to be the talk we would have liked to have attended when we were, say, back in April of last year, April of 2011, when we were growing really fast, still really small, just 2 engineers. And we didn't know a lot of the answers. There were a lot of promises out there, but we didn't know which ones to choose, which ones were good, and which ones would be death. So I'm going to jump right in. And this talk actually may need to scale up a little bit now that more people know about Pinterest, but I've been giving similar versions of this talk for about a year now. So I'll tell you a little bit about Pinterest for those who don't know. Pinterest is an online pin board to organize and share what inspires you. It's a social network. We have the usual set of actors. We have a user. This is my profile page. I have boards, which are organizations of pins. And pins are an image with a little bit of metadata, a lot of metadata. One is a link, which links back to where you found this image. If it, for instance, is from Etsy, it might link right back to a product that you can go buy. It also has a description at the bottom, which describes why this image is important to this user. You can also follow people. So I have 2 people I'm following, Matt Jones and Susan Peck here, that you, among others. And when they post a pin, that pin goes into my feed. So I can also follow boards, individual boards rather than whole users. So let me get your brains into database mode. We have users. Users can follow boards, and users can have boards, and boards can have pins, and you can have users who follow users, who follow boards, and we also have other relationships, such as I can go and repin your pins, which means I get a copy of your pin, not a reference, and I can also like your pin, which gives me a reference to your pin. So let me go back to March 2010. This is when we launched the site, when it became available. So that looked like we were on Rackspace. We had 1 small web engine, 1 small MySQL database, and 1 engineer. And this is maximum flexibility when you're trying to make whatever it is you're making. You don't have a lot of moving parts, and you don't even have enough that much traffic. So forward to about January 2011, and from March 2010 to about January 2011, we were, as our founder described, we were in stealth mode, but we didn't want to be. So January 2011, the design was pretty much done. It hasn't drastically changed since about that date. And we had moved to Amazon EC2, had our images all hosted on S3, fronted by CloudFront, an Nginx box, 4 web engines, mostly for redundancy, MySQL database, and a read slave. A couple task processors, a MongoDB engine, and 2 engineers. And then what happened from January to about September was we went on this wild ride. And it doesn't matter what scale you're at. When you're doubling every month and a half, things go nuts. You don't get any sleep. Everything's breaking all the time. And there's all these people coming to you with fantastic promises. Use our system, and all you have to do is add a box, and then you're done. So when that happens, you're not meant to read this. You're mostly meant to be frightened by it. You just end up with a whole glut of technologies, each of which is breaking in their own special, unique way. Just as like a quick rundown, we've got MySQL, Cassandra, Membase, Memcache, Redis, task processors, which was Celery and RabbitMQ, Elasticsearch, Mongo, and we only had 3 engineers. The primary there being MySQL, and even that was running really hot. All of these were running to their edge in almost every way. So we went on a major lesson 1. It will fail. If you take in a piece of technology, it will fail. So keep everything simple so that you don't have to deal with lots of failing pieces. So fast forward to January 2012, we did a full re-architecture of everything we had. We asked lots of questions about what actually seems to work. And we changed our whole system to make it simpler. And what we ended up with was we got rid of most technologies, and all we really have for our main data store now is MySQL. We have Redis and Memcache sitting on top of that too, and that's it. And at this point, we had 6 engineers. So getting a little bit easier, a few more people on call, a few more people to look at different pieces of the system. And this system has worked. Going to May 2012, I don't have this updated quite with the numbers for today, but we have just increased the number of boxes. And that's sort of, the holy grail of scaling, is getting to the point where you can throw money at the problem. We now have 135 web engines, 75 API. This is back in May. I think it's maybe another 50% on top of that. 80 MySQL boxes, 110 Redis, and 60 Memcache. And at that time, we had 25 engineers, and now we're maybe about 40 or 45. So it's many more people to round out the whole system and look at every problem with a finer eye. So I'd like to talk a little bit about what worked and what stuck with us the whole time. Amazon worked very, very well. It has good reliability. I know that there's been a couple of things. It's not quite as good as a data center, but it's pretty good. So you do make your system tolerant to problems. The reporting and support is very good. They also have these great peripherals. So they're not just instances. You can get a managed cache. You can get load balancing, DNS, MapReduce, all these little things that can help you grow your company without having to have somebody who really understands the in and outs of say, a database or other pieces. So for instance, we're still using their DNS. We're still using their load balancing. It's really convenient. And their MapReduce is also really convenient. It means we don't have to have somebody maintaining a Hadoop cluster. Most importantly with Amazon, and probably I guess with any clustering, any cloud system, is that we can have a new instance up in seconds. And that was crucial. When you have 2 engineers and you need a cache now, you don't want to wait 3 weeks or 4 weeks. You'll be dead. So when we need to bring up 5 caches, we can have them in about 10 minutes. If we want to bring in another 80 databases, bringing them up takes about 10 minutes. There's a replication lag and all of that, but it's really, really fast. It means that we don't have to spend a long time focusing on planning. There's a con. You have limited choice. So if we wanted to get 256 gigs of RAM for a database and at the time a large SSD, although it's not true anymore, you didn't have the option. You only had probably about 10 flavors, so you had to choose from those. But the pro of that is that you have limited choice, which means you have to work with what you're given. It also means that you don't have 50 flavors of boxes, some with this front side bus and some with this kind of cache, and maybe this one fails in this subtle way because of the firmware. You have only the same set of boxes. And you tend to use them for all of them. So all of our databases are the exact same type of CC2 cluster instance. It also means that you just are forced to use these boxes, so you know what your engineering roadmap looks like. Okay, we're going to be using this box. There's no question. That's what we have. So why MySQL? MySQL is the core, the rock of our system. It's extremely mature. It's been around for 27 years, and I think for the last 5, 6, 7 years, it's really, really become the most solid database around that's free. It's well known and well liked. This is very important. If you're hiring an engineer or you're looking for people, they will all have used it. Some will even have used it in a expert capacity, and some will even have probably developed it. And they'll like it. They'll have no problem with it. There's rarely any catastrophic loss of data or any loss of data. I don't think we've ever lost any data on MySQL except when a box goes down that we were not properly backing up. So it's our own fault. Response time to request rate increases linearly. This is also great because it means you can predict what's happening tomorrow. If you increase your pressure by 10%, it seems like the request rate goes up proportionally to that. Other technology, if you go past some magic threshold, you dive, and your response time goes from tens of milliseconds to seconds in a matter of hours, we've seen. But we've never seen that with MySQL. Very good software support. There's extra backup, which gives you online backup, which means you can bring on a replication slave without shutting anything down, and you can back up nightly. InnoTop for seeing exactly what's going on inside your system. MatKit for profiling. There's an active community. If you have a problem, somebody has answered it. Go to Stack Overflow. They've got the answer, and several layers over, plus lots of conversation where people are insulting each other over and over again. Very good support from places like Percona. They also have their own version of MySQL. And there's companies like Facebook, which keep pushing patches down. So really MySQL is being pushed at the front of technology. And it's free. This is kind of an important metric before you have venture capital. So we were building the system before then, but I wonder if free were not a constraint, we may have tried something like Oracle or DB2, but I've been very pleased with MySQL. So Memcache survived. I like Memcache a lot because it's very simple. It's extremely mature. It hasn't been around as long as MySQL, but it's such a simple piece of software. It's a value-added hash map. It's a hash map with a socket attached. It's well-known and well-liked. Everybody's used it. Even people who are kind of in places where they don't use any technology outside their own, they'll still use Memcache, such as Google. Or they'll get the concept. It's just a key value store. It never crashes. It has very few failure modes. The only one I know of besides hardware failure is if you give it too much RAM. So, user failure. And it's also free. And finally, Redis. Redis is sort of a newcomer, but it has worked really, really well for us. If you don't know Redis, Redis is a key value store. It's like Memcache with a couple of nice little tweaks. It has distinct data structures. So you can get a list, you can get a set, a sorted set, you can even have pub sub and hash maps, hash tables. It also has persistence and replication. The neat thing about its persistence is if you want to, you can snapshot. So it's a little bit more reliable in that you're not reliant on your hard drives failing. Hard drives on cloud tend to be a little bit dicier because they're multi-tenant, so somebody can show up and run some massive I/O job and drown out your database. You also get replication, which is great if you need a little bit of extra reliability. It's well known and well liked already. There's a great community out there. The developers who are making it are also very responsive. There's few failure modes. There are a few more than MySQL and others that just and Memcache would just never seem to fail on us. But you just have to be mindful of them, know the little quirks, and it's also free. And I love free. So back in September, when we decided to do this re-architecture, we asked ourselves, what technology should we go with? And first thing we realized is that there's not really a good nomenclature to describe the lay of the land. So what we came up with was we described clustering to really mean, I guess, sort of what people call NoSQL. It's the automatic build everything out for you solution where you don't have to do anything but add boxes and plug them in. And then there's the sharding solution, which is the manual full control approach where data sits in one place and never moves. And then there's sort of in between. So we describe a spectrum where clustering data is distributed automatically. Data can move between at almost any level, between nodes, between logical nodes and anything below that. Rebalances, you rebalance your data to distribute your load. So if you bring in several new boxes, you can do a rebalance and it'll just mush the data across all the boxes. And nodes communicate with each other. Typical cluster nodes are all symmetric and they have to negotiate with each other to determine who should, determine if one of them has too much load and if one should steal some work. On the opposite side is sharding, where data is distributed manually. You actually decide where everything goes. Data does not move once it lands. If you're talking in the purest sense of sharding, once something lands in a shard, you never move it. To add more capacity, you split shards, or you expand to other shards that you haven't opened up yet. And nodes are not aware of each other. These are just dumb nodes. Almost you could think of them as key value stores with indexes. And then there's a bunch of technologies that sit in between this. You can take almost any technology and throw them somewhere on this graph. And also, not just database technology, but different companies' sharding approaches. Different companies fall in different areas depending on if they want to have a service for generating UUIDs and other generation services. So we ask ourselves, why clustering? Some examples of this are Cassandra, Membase, HBase, Ryak, Mongo, the ones that are a little bit more automatic for you. They automatically scale your data store. They're easy to set up. I think some of these, we downloaded an Amazon AMI and we flipped it on and it said hello within 5 minutes and we started talking to it. It was kind of crazy and it really leaves a good feeling. You're like, okay, everything's gonna be okay. Don't know if you guys know where I'm going with this. They can spatially distribute and collocate your data for you. So if you need to have some in a data center, for instance, in Virginia and the West Coast in Malaysia, they'll help you with that. There's high availability because you've got a bunch of nodes. One goes down, in theory, everything's replicated, so it's okay. There's load balancing automatically out of the box, and there's no single point of failure, so you don't really need engineers at this point. So I'm going to have to ask, what could possibly go wrong? Well, so what we ran into, and I'll describe a little bit about our experiences trying these technologies, is ultimately they're still fairly young. MySQL has been around for 27 years, and it's pretty complicated. These things have been around for, I think, just less than 10 years, and they're much more complicated than MySQL. The algorithms that are described, especially when you do symmetric negotiation, are extremely complicated. If you ever look at Paxos, look at Leslie Lamport's simplified Paxos, you'll be frightened by the end of it. There's less community support because there's a lot of them and because many people haven't used them heavily in production. There's not a lot of places, if you go on Google and search Cassandra, you may or may not find anything. Some of these groups don't even have a community as far as I can tell. Fewer engineers with working knowledge. If I brought in one of these technologies, I'd really kind of have to hunt for somebody who knows this technology. They're difficult upgrade mechanisms. I remember once we were going from like a 0.001 release, like a 0.812 to 0.813 release of some technology. I can't remember which one it was. And there was all this description of, okay, you need to bring down this part and bring it up carefully and then watch everything and then maybe just bring down the whole thing and then bring it all, and just the descriptions are really kind of frightening, and I'm amazed that it worked in the end. Actually, at one point it didn't. And I actually lied to you. There is a single point of failure in this in clustering, and I'll describe it right here. It's a very big one, and it's probably the one that pretty much took us down several times. Here's your happy cluster. Everything's green. Life is good. Then one goes red. It's okay. It's okay. I've got another one. So you bring in your other box, and your cluster automatically moves everything over. So where's the problem? The problem is the cluster management algorithm that sits on every one of these boxes. It's the brains behind where everything should live, all the negotiation that goes on. So suppose you have a cluster of 100 boxes, and there's a slight bug in this cluster management algorithm. Well, that happened. We had about 4 failure modes I'll describe, and these are ones I've heard from all different other people at other companies with different technologies. Data rebalance breaks. So you bring in a new box, you hit the magic button, and your data starts moving over, and then it just stops. And what do? Well, you start nudging it, you stop it again, try restarting it. It's 2 a.m., and by 6 a.m., I've moved it all into MySQL memcache. Okay, not that it describes an exact story. Data corruption across all nodes. This is probably the most epic. We had something spray a little bit of corruption across all the nodes, and then some of the technology underlying each of the nodes stopped, and then our response time started rising because various cleanup mechanisms also stopped, and we had a CTO come to us and say, I'm sorry, all your data's gone. Fortunately, we've only ever used MySQL for our golden copy of data. We've never used some of these technologies for the golden copy. They're more for metadata, for counters and things like that. So we had to rebuild all of our counters. Improper balancing that cannot be fixed. This is my favorite. Suppose you have, what we commonly see with some of these is you'll have 99% of your load in one of your boxes and 0 to 0.1% spread across 10 of your boxes. Okay, that's kind of irritating that the automatic thing broke. Sometimes you can manually move over data. Okay, that's great. Okay, so at least we've got a tool to fix it. So you start moving over your data, and then what happens is the thing's so smart, it moves it all right back for you. So that was really irritating. And then final one is data authority failure. I also really like this one. This one's neat. You bring in you start bringing in a secondary or another box that's supposed to replicate one of your other boxes, the primary. So primary is 100%. Your secondary is kind of rising. He's replicating off the primary. He's at about 80%, and suddenly decides that it's the primary. The previous primary says, oh, I must be the secondary then, because there's already a primary, and they swap. And now you only have 20% of your data. Oh, sorry, 80% of your data. You've just lost 20%. That was a neat 3 a.m. surprise. So we learned a lesson. Clustering right now is scary. I think it's such a new technology, and it will be the future, but right now it's still dicey, and everything's changing really fast. So I can't quite speak for today, but I'm still, because we've been off of them for several months, but I'm guessing it's still the same story. There's just a lot of risk. There's also a lot of risk in that with clustering, so many things are automatic that you don't really get in deep with your data, and I think that's important. So same question, we asked ourselves, why sharding? You split your databases to add capacity, so you can grow. You can spatially distribute and collocate your data in the same way that you can clustering. It's just a little bit more manual. You have high availability and load balancing, which is the main reason we do this. But also important is that your algorithm for placing data is very, very simple. You still have a single point of failure, and it is that algorithm, but instead of it being a complicated Paxos negotiation kind of algorithm, it's like 10 lines of bit twiddling, at least in our case. It's really, really simple. And ID generation 2 is very, very simple. So to describe when to shard, I'm going to bring up Yash. He's going to jump into a little bit about if you shard too early, what can happen, and if you shard too late, what can happen.
Cool. So we were stuck with the question, like, when exactly should we actually shard our data, since we have an infrastructure that's failing every single day? The latencies keep spiking up during our peaks. So actually, we found the answer pretty late, because like the answer is like if you just approach sharding way too early, you pretty much like burn your schema down and denormalize your data across all the shards, and adding features is kind of a big pain. On the other hand, if you just like shard late, just like us, like you have a huge, humongous piles of terabytes of data that's sitting in your own infrastructure that should be moved into the new schema across all your shards, which takes like a couple of months to actually transition properly and verify the authenticity of the data. So like before even you approach sharding, one simple solution was like just lock down your schema and do a feature freeze for a couple of months and just approach the sharding just like we did. It worked pretty well for us in our case. So like here's how like we approach sharding. Like solidify the site design, work with your product managers, and like lock down all the features we're going to support for the next couple of months, and make sure your backend architecture is functioning properly. Remove all the joins and complex queries, because like pretty much your data is going to be distributed across different physical servers, and you have to pretty much do the join instead of relying on the database for you to join. Add as much cache as possible and go to the database as less as possible. And still you are having a lot of problems, then you can actually do a cheap sharding, which is functional sharding. In our case, like we have a huge table of pins. Like there were like hundreds of pins coming every second. So we actually took our largest table and put it in its own database, and then like the site would just function properly till you run out of memory for the indexes. And then if you're still growing, then I think you should bite the silver bullet and shard. So here's how our transition roughly looked like. Initially, we had a single database with all the proper normalized schema. Then we slowly denormalized and like remove all the foreign key relationships, added a bit of cache. Then this traffic still started to grow. Like we brought a lot of read slaves and pointed the application to the read slaves to do the reads and write the writes to the masters. And then we actually functionally sharded, which we picked the largest table with the highest load and then moved it to its own database, and thereon add a lot of read slaves and then throw a lot of cache. And then finally we did the real sharding, which was just partitioning your data across all the physical nodes. So a couple of things to watch out is like you cannot join your tables because your tables are now functionally sharded. And there's no transaction capability. So like if you have a bunch of writes across different tables, you cannot do a transaction because there are different physical servers, and any write to any single server can fail. So that's something you have to watch out for. And then to maintain unique constraints, like you need unique username or unique email address over all your users. That requires a special extra effort. And schema changes requires a lot of more planning because you have the same schema replicated over all your shards. And generating reports is a little more extra work because you have to run your report queries on all the shards and then do an aggregate, and then email the reports. So the question is like, how did we exactly shard? So when we were actually approaching this problem, we took a close look across various sharding approaches, various sharding topologies on the internet, and like we took a look at the Cassandra's ring-like structure. We took a look at the Twitter's Gized approach. We spoke with Etsy folks and Facebook folks, and and we made a bunch of notes. And one point that actually struck us was like, the less data you move across the shards, the more stable your architecture remains. So with that takeaway point, we actually architected our system such that like we never move our data across shards. So we sharded to the foreseeable future with having like, we pre-sharded each MySQL database to have a small subset of data, and then we split the databases across huge load spikes. So here's how our initial sharded topology looked like. We chose 8 physical servers, cluster compute instances, and we put 5 MySQL databases on each physical server, and like, and then for high availability, we ran all our masters in multi-master mode. So during failures, we swap the application to read to the other master, and then we bring a replacement master into the different availability zone. So once we see an increased load on the database, we do our matkit profiling. We see what kind of features were pushed in the last couple of days. We see if there were optimized queries, or like, was there proper caching in place. And once we sweep across all these problems, and if we still see a lot of DB load, then we call this as shard splitting. Like we spawn 2 different slaves in different availability zones from a single master, and then we flip the application to point like, oh, this shard range exists in this master, and this shard range exists in a different master. And we cut the replication pipe from the master. And from now on, we have 2 different masters for the same shard range. And that's how we keep actually like sharding for the foreseeable future. Couple of things. So early on, when you actually shard, different sharding algorithms like have mapping tables to denote like, hey, this piece of data exists in physical shard A, and another piece of data exists in physical shard C. So like pretty much all the sharding approaches have one thing in common, that's called mapping. So since we were on AWS for like a long time and we didn't have any plans to move around, we took a look at the average MySQL query latency, and it was around 7 to 8 milliseconds. So when we were designing the architecture, like we were like debating like, hey, where should we store this piece of information for mapping to denote, like, to tell us where a piece of data exists. And when we actually built the tables, like we just thought like, hey, just to know where a piece of data is waiting for 8 milliseconds really worth it? And we thought like, no, maybe not. So we designed an ID structure with 64 bits, where a bunch of bits are allocated for the local ID, which is the table auto increment, and a couple of bits for the table to denote the table name, and all the other bits for the shard ID. So we pretty much brought the mapping table right into the ID structure. So if we have a bunch of IDs to look up, we actually decompose each ID, and then we know exactly where this piece of data is, and thus we avoided a MySQL query to determine where a data goes. So we have a lookup data structure in our app server to denote like where each shard exists and how it maps to a physical server. And the shard ID denotes the database name to go into the MySQL, and the type denotes the table name to go to, and the local ID denotes where exactly in the table is the piece of information we wanted. And that's how our lookup structure looks like. We're a big Python shop, so that's a dictionary, a hash table with the key name as the physical server and the value as the shard ranges. So the shard 1 to 512 exists on 001A, and while 513 to 1024 exists on 2B, and thus forward. So once we get an ID and we decompose the ID, we have a shard ID, we have a local ID, and we have the type. So in this scenario, we are looking up a user. So that user falls under ShardDB 03A. So we go to that database and we select the user table, and then we get the serialized data to grab that user's data. So a little more regarding the ID structure, like whenever there's a new user on the site, we select a random shard for the user and register that user onto that shard. And once we choose the shard and perform a MySQL insert, we get a local ID, and we know that the table name is user, so that'll be like 2. And we know the shard ID is some 1023, and we gel all this together, and we form a global unique identifier, which is a 64-bit ID in this case. And just to fetch all the users' data in like one single lookup, we co-locate all of users' data in the same shard. So like if I were to pin something on Pinterest, all my pins would co-locate on my shard. Thus, to render my profile, all you need to do is to just go to my shard, query the user table, query the board table, query the pin, and like within 3 MySQL queries and one shard connection, you can pretty much render all of my data on the user profile page. Local IDs are assigned by auto-increment. We all know MySQL auto-increment just works perfectly out of the box. We never had any issues, so we chose to stick with it. And one of the tricky things is like allocating enough shard ID space is one of the bigger decisions we made. So we left around 65,536 virtual shards, which is pretty long way to go. You can actually have 65,000 MySQL servers to go to the brim of it. Initially, we chose to only open 4,096 shards because like having 4,000 databases is a kind of a long way to go. And we didn't want to have like so many small databases in MySQL and just eat up the drive. So we chose a small range and we open, and once we believe we have enough data for the next 5 years, we would shut down this range and open a different range and let the new users go to the new ranges, and thus we keep expanding horizontally. So pretty much every piece of data in Pinterest architecture either falls in one of these categories, an object or a mapping. An object is something like a noun, a pin, a user, a board, a comment. Pretty much all these things are an object which defines something about the object. All our object tables are pretty much local ID, which is auto-increment, and we have a JSON blob. We borrowed this approach from friend feed for one reason is schema migrations. So what if tomorrow, like Marty comes over to me and say, I want to add something on the user table. We need to run an alter. So alter pretty much locks up your table for writes and causes downtime. So we chose this MySQL blob approach where you put serialized thrift or JSON objects. So if you need a new attribute on the user object, all you need to do is go into the code and say like, hey, this is a new attribute called about, and it's a string of 4,000 characters or something. And the app code would do the proper validation and write it to the database, and pretty much zero downtime. There's no need to run any migrations across your shards. And we have mapping tables to denote mapping across 2 different objects. So in this case, a user has a lot of boards. So we have a user has boards table to denote the user ID and the board ID. And you would perform a query on the primary key, like you select star from this table where user ID is this, and you would get all the board IDs from the table. And similarly, pin has likes, and pretty much every mapping has 2 different object types and a sequence ID to denote the timestamp at which this write happened. And we followed this naming schema, like all the object tables have nouns, like boards, users, and all the mapping tables has noun, verb, noun to denote the kind of relation between the 2 objects, like user has boards, pin has likes, user perform likes. And pretty much all our queries are either a primary key lookup or an index lookup because we pretty much denormalized all our data and brought the queries better down to the metal. And the data does not move across shards because the unique identifier generated for each object is married with the shard ID. So you cannot really move the data across shards, but you can actually move the shards altogether to its own physical data server. And all tables exist on all the shards. We have a perfect symmetrical sharding, and there are no special tables. And we don't really require schema changes because a schema change is pretty much either adding a new attribute onto the serialized data or creating a new table and writing to the new table as the mapping is required. So we can see an example how we perform loading the user profile on Pinterest. So that's my profile over there. So if you go to pinterest.com/Yash, like we go to the user table. No, first you go to the username to user ID lookup, which is a global, which is not a sharded table. It has its own database with all the unique constraints and indexing. You go to the table and ask, give me the user ID for Yash, and you would get the user ID. Then you would decompose the ID, select the shard. You would go to the shard and get the user object to get my name, my picture, my about, my Twitter links, and all that. Then you would go to my user has boards table, grab the board IDs. You would go to the boards table, grab the board data. You would go to the board has pins table to grab a bunch of pins. And then you would go to the pins data and grab the pin metadata. So it looks like a lot of MySQL queries to render this single page, but each query has a memcache or a Redis cache associated with it. So mostly you wouldn't need to go to the database to render this page. All of this data can be like fetched from the cache. And we have proper offsets and limits just to make sure, like a user with 1,000 boards, we won't just render all the 1,000 boards. We would render like 50 boards and do a proper pagination. Scripting. So this is one of the important feature of the sharding, I would say. Like when you have this huge old infrastructure with terabytes of data and you have designed a new architecture with the sharding, moving your data from the old to new is a pretty tricky job. Although it might sound very straightforward, like, hey, we can just like write scripts to move. Doing it with zero downtime is a kind of big challenge. So initially when we approached this problem, we wrote app server code such that when a new pin comes in, we write to the old architecture, get the old ID, and write to the new architecture, get the new ID, and we would maintain a mapping of like, this old pin has a new pin ID of this. Just to make sure everything is scripted, you need to note like, has this pin moved from the old to new architecture? It's kind of a lot of my database writes, but I think you have to like take this hit and go through that ugly scenario phase of writing to two different architectures. So the quicker you do this, the better off. But we made a bunch of wrong assumptions, like we can actually move all our data in like 3 weeks or 4 weeks, but it roughly took around 4 months to completely move our data across shards and perform validation checks, like every piece of data was moved. So during this phase, we learned our bunch of lessons is to like build your own scripting farm. We were running on RabbitMQ and Celery, which was the Python message queue. So it was pretty heavy in size, and once you put it like millions of jobs into RabbitMQ, it just crawls. It's very slow. So we built a new scripting farm on top of Redis. We all know Redis list just works fine. So we were inspired by GitHub's rescue queue. There's a blog post on GitHub blog. So we built a Python clone. I mean, we took an open source project, which is a Python clone, and adapted it to our requirements. It's called Pyres. So whenever a new pin comes in, we would do the old write, spawn a job to do the new infrastructure write, and then return to the user. And the workers would pick at the later time and create the new pin and write to the mapping table. And we have another bunch of scripts to make sure every pin has a new pin ID in the legacy mapping tables. But trust me, it's a pretty big thing, and we made a lot of mistakes, and we learned from our mistakes. To actually script is a big pain. You have to have a bunch of sweeping iterations. Like the first iteration looks like it's completed, but trust me, only 95% of your data goes through. There's still a lot of rows that were never. So it's like a sweeping couple of runs of the same script, and then you can totally assure like all of your data is moved. Couple of things we are in the works are we are moving to a service-based architecture because we have this huge, humongous app server code that connects to every memcache and every MySQL shard. And these are multi-threaded, so each thread actually uses a connection pool, and we're spawning like thousands of connections to a memcache and thousands of connections to MySQL, and each connection has around 8 kilobytes of RAM inflation inside of memcache and MySQL. So one thing we're trying to do is we're going to move to a service-oriented architecture where we'll build like search as a service and users as a service, something like that. That way, if we need a user, all we do is make a thrift call to this service, and the bunch of boxes dedicated for this service would only connect to the proper memcache and bring down the connections, and they would serve the data which we need. A couple of advantages is you get an isolation of functionality. It's like if there is a bug, like, hey, when we ask user X, why are we getting user Y? You can actually like go to the exact piece of service, exact service, and then debug it right in that service. And you can get dashboards just for the service, and you can pretty much see like where most of your latency or where does most of your time is spent. And another thing is isolation of access. So you don't need to give all your production access to all the employees, all the engineers. You can basically shard them into the teams and give the team the service they own. And scaling the team would be much easier. Thus, we learned our third lesson is like keep it fun, keep it simple, because things are gonna like break and you're gonna go through a huge ride. With that, I want to conclude, and just to let you know, we are hiring. If you're interested, come talk to us after the talk. And with that, I want to open up for questions. Yeah.
It sounds like you're using two caching technologies, Memcache and Redis. How do you decide which goes where?
So the question is, when do you decide to use Memcache as a cache and Redis as a cache? Do you want to take that?
So there's a couple things that, is this working? There's a couple things that come into play there. One is Memcache ultimately is just rock solid. I think there's, I love Redis, but we do have a couple of extra issues with Redis, and Memcache is just down to the core solid. It also has a little less overhead in terms of connection size. And then also, depending on what you're storing, Redis can take more RAM. If you're storing lists, you might be better off serializing in Memcache, depending on your requirements, than putting it into a full doubly linked list inside Redis. Redis does do a few optimizations, but we measured, and I think the increase in size between a serialized list in Memcache versus Redis was anywhere from 2 to 9.6x larger. So it's really about, we love Redis, and it's got a lot of great toys, but Memcache is just, it's just so solid and so simple and so down to the metal.
Well, what do you use Redis for?
Couple.
Oh, sure. Question is, what do we use Redis for?
So to actually exactly answer that question, like we cache all the objects in Memcache, and all the mappings going to Redis. Because let's say you have a bunch of boards and you add a new board. Instead of invalidating the cache, we store your board IDs in a list, and when you create a new board, we do an L push. And thus, we are actually updating the cache. So when you delete a board, we just like pop that board ID. So that's how Redis has been a great advantage to us. So to answer, like all the mappings are cached in Redis, and all the objects are cached in Memcache. Sure. So the question is like, when exactly do we decide to build a service? Okay, to be more specific about our services, cache as a service or database. Do you want to take that? Or?
I think I understand the question. Are you asking about specifics on when we decide to construct a service and what belongs in that service?
So basically, we have three services to answer that question. One is search, the other is follower relationships, and the third is feeds. So whenever we have a new piece of data, we spawn a job on the queue, and the worker would pick up the job and write to the search service, like, hey, here is a new pin, here is a new user, here's a new board. That's one service. And whenever there's a search query, we query the service, And then we get the data, then we do the cache lookups, and then render the page. The second one is follower. So whenever there's a follow or unfollow, we would make a service call. The reason was there were a lot of follower caches, and there was a lot of app servers connecting to follower. So the follower was a kind of different data, which was very high write throughput and very, very high read throughput. So we decided to attack that piece of data in a different service way. So we used Redis and all that stuff. So we built a service on top of the Redis sorted sets. The third one is user feeds. So whenever you pin, all your followers should see the piece of data. So you would spawn jobs, and the job would query all your followers from the follower service and distribute this pin to all the followers. So that's one service. So we really don't have a concrete answer to say like this would be a service, but based on a lot of problems we would see, that a lot of latency, a lot of connections, we would make a call whether like, hey, is this a service, and do we want to do something different in the future? So, sure.
Sorry, say that again?
Business reporting across
Oh,
cross shards.
Oh, yes, yes. So business reporting, there's two approaches. We can spawn scripts that go across all of our shards and ask a question on every shard, and that's actually very effective. But mostly at this point, we're using Hadoop. So every single action on the site gets logged down to through a service called Kafka that's written by LinkedIn, gets funneled through that, and then copied down to S3 for consumption by Hadoop. So most business data goes through that. And then also I think we do a snapshot of different databases each day, and also feed that through Hadoop, so we can do joining between the tables at the MapReduce level. Does that answer your question?
You mentioned there's some quirks with Redis. Can you elaborate?
Some quirks with, the question is, there's some quirks with Redis, and this have to be the last question, but we'll hang around outside if you guys have more questions. So quirks with Redis. So when you do replication with Redis, the way Redis does a background save is it forks itself, and then it does copy on write. So if you have a lot of load coming in, you can double the amount of RAM you actually need. And sometimes you start hitting swap. So it's a little dicey. If you get past 50% of your RAM, you're starting to push into risky land. We typically run around 70 to 80% of RAM before we have to split again. So that happens with replication, and also if you want to do a database, if you want to do a BG save periodically to snapshot your data. Other things that we've experienced that have gotten fixed over time, and this is just really a maturation issue. We've had a couple of data corruption bugs. We've had a couple of, there was a bug with Ubuntu's 10.04 kernel that would mean that we had a lot of I/O and we didn't know why. Next 11.04 was fine. So it's just really a maturation thing, and pretty soon it'll just be really solid. They're still iterating on new features, so until the features are frozen nearly completely, there'll still be a little bit of diciness. Thanks for coming. We'll be outside taking questions, and please come to us if you're at all interested in working with us, because we need a lot more people. At the rate we're growing, we'll probably be at about 7 million people in just a few more years.